Good day, everyone. So, we will be continuing our discussion on intelligent systems, specifically in the branches of the intelligence or intelligent systems. Now, so here's the outline of our presentation. We will discuss what deep learning is, the neural networks, the basis of neural networks, artificial neurons, neural network architecture, and some of ethical considerations. Okay, so let us discuss what is deep learning. So deep learning is a subfield or submodule of machine learning. Okay, it involves the use of neural networks with multiple layers. No? Actually, it is called deep neural networks to model and extract intricate patterns from large data sets. No? The term deep refers to the multiple layers through which the data is transformed and processed. Okay, that's deep learning. Again, it is a subfield of machine learning that involves the use of neural networks with multiple layers to model and extract intricate patterns from large datasets. The term deep refers to the multiple layers through which the data is transformed and processed. Okay, so here are the key components of deep learning. We have the neural networks and the layers. No, so the fundamental building blocks consist of interconnected artificial neurons that mimic the functionality of biological neurons. So that's neural networks. Next one is layers. So layers, now deep neural networks consist of an input layer and then multiple hidden layers and an output layer, allowing the model to learn hierarchical representations. So meron tayong input layer and then magba-branch out siya into multiple layers, and then there it will get an output layer, no? So that the model, no, it allows the model to learn hierarchical representation. So multiple layers yan kung makikita nyo. Para siya talagang biological neurons, no? Itong artificial neurons na to. And then its applications, it has been successfully applied to various domains including computer vision, natural language processing, speech recognitions, and reinforcement learning. So ano ba ang significance ng deep learning? Okay? So deep learning has significantly advanced the state of the art in artificial intelligence, leading to breakthroughs in complex tasks, no? Such as image and speech recognition. Okay, so that's the significance of deep learning. So ano ba ang visual representation nito? So it includes a simple diagram illustrating the architecture of a deep neural network with multiple layers. So later on sa mga video na mapapanood natin, ipapakita sa atin yung neural networks and how it works and how deep learning or artificial intelligence gather data and then continuously spread throughout the layers, creating new artificial neurons. Okay, so let us watch the following videos, no, that I have researched. No, here's the first video.
Deep learning powers most of the technologies that we rely on every single day. This could be machine translation that translates the websites that we're visiting. It could be facial recognition that lets us log into our phones. Or it could even be recommendations that we rely on to show us the next best TV series or show on Netflix to watch. So in this video, we will look into deep learning in more detail and really understand what it is. This video is part of the Deep Learning Explained series brought to you by Assembly AI, a company developing a state-of-the-art automatic speech-to-text API. If you'd like to have a free API token, follow the link in the description. First and foremost, a description of deep learning. Deep learning is a group of techniques that are based on neural networks that have the capacity to learn complex patterns directly from the data. So let's break this down and go at it step by step. First thing, neural networks. Neural networks are algorithms that were created inspired by our brains. You can see in this example, we have layers of neurons stacked one after each other. In neural networks, we have three different layers. One of them is called an input layer, where we accept the input. The other one called an output layer at the end of the network, where it gives the actual prediction or the outcome of the network or the algorithm. And in between, we have the hidden layers. All of these layers consist of neurons. Depending on the input or the output of the problem you're solving, you're going to have different number of neurons. There is always one input and one output layer, but the more hidden layers that you have in between those, the deeper a network that you're going to have. And that's where the keyword deep comes from in deep learning. Whereas learning comes from machine learning, or the fact that this network is able to learn different complex patterns. Neural networks and deep learning has been heavily impacting our lives in the last 10 to 15 years, but actually they've been around for longer than that. The first neural network was suggested all the way back in 1943. And since then, there have been waves of interest that eventually died out. And you can actually think that we are currently living on a new wave of interest when it comes to deep learning. And this time, people think that it's not actually going to go away because, first of all, we have a lot of data that we can deal with, and the computing power is getting better and better every day. Well, not to mention the research that is being done into deep learning currently to make it better and faster every day. So let's talk about how this all relates to machine learning and also how machine learning compares to deep learning. Let's start all the way from the top. We know that we have computer science about everything, right? And computer science has different branches. This could be computer security, software engineering, or distributed systems, for example. And one of these branches is called artificial intelligence. In artificial intelligence, the general goal is to have the computers perform tasks that are normally typical to humans in a way that is accurate and also efficient. There are different approaches to artificial intelligence, of course, and one of these approaches is called machine learning. In summary, machine learning aims for the computer to learn how to do a task directly from the data. Well, deep learning is part of machine learning. It's, again, in itself a group of techniques that are in machine learning. So when you say machine learning, you are actually including deep learning inside the picture. But when we want to compare machine learning and deep learning, of course, what we're trying to compare is the traditional machine learning algorithms with the deep learning algorithms that have been improved in the last decade. All right, so let's look into how they're different. Traditional machine learning algorithms on one side and deep learning on the other side. So the first and most prominent difference is that when you are training machine learning algorithms, you need features extracted from the data manually. And when you're doing deep learning training, you don't have to do that. So just to give you an example, let's say you're trying to classify cats or dogs, the most common example on the internet. So what happens is when you want to train your model to understand if a given picture is of a cat or a dog, you have to extract features such as how many pointy ears it has, what does the nose look like, what is the color of the nose, what is the pose that the animal is giving, for example. This is just an abstract example of what kind of features that you can extract. Whereas for deep learning, you can just give the image as it is to your deep learning algorithm, and it will itself understand what the pattern is and what the features are that are separating the two animals from each other in these photos. And this is very nice, right? Because when you're training deep learning models, you do not have to do feature engineering at all. But of course, this nice little feature comes with a cost. When you're training deep learning algorithms, you have to have much more data than you need for traditional machine learning algorithms to be able to train your model to be accurate. And also, due to all the computation that needs to be done in deep learning algorithms, you have to have a stronger machine, which has higher processing power, and it's going to take a longer time. But that's kind of like a trade-off, of course. The stronger the machine that you have, the less time it's going to take. But on average, it's always going to take longer to train deep learning algorithms that compared to the traditional machine learning algorithms. But there is one other difference, actually, that is kind of hard to put on paper. And that is that deep learning algorithms are actually able to capture patterns that are a little bit more abstract. So you can actually perform tasks with deep learning algorithms that you would not be able to with traditional machine learning algorithms. This could be, for example, natural language processing. You might not always know what kind of features to extract or what kind of features to generate from your text to be able to do sentiment analysis, that is, analyzing if a given text has a positive or a negative connotation. Whereas deep learning handles this very well just by looking at the examples which were labeled. Another example is actually the example that I've given earlier. When you're trying to distinguish between cats and dogs, it might be a little bit hard to create features just by looking at the animals' photos. Whereas with deep learning, you don't have to worry about that. You can just feed your data into the deep learning algorithm and then it will extract everything for you. So I think this makes deep learning algorithms better when it comes to abstract tasks, which would be really hard for a human to even format. And there are, of course, other cool things that you can do with deep learning. For example, turning speech to text. And that's exactly what Assembly AI does. So if you're currently interested in having a speech to text API integrated in any of the projects that you're working on, you can give Assembly AI a try. You can follow the link in the description to get your own free API token to start working on it whenever you like. If you like this video, please give it a like and maybe even consider subscribing. We will be here every week bringing you information on deep learning, machine learning, and tutorials on the latest technologies that are out there. We will be very happy to see you with us. If you have any ideas of videos that we can make, definitely go ahead and write a comment and let us know. That would be awesome. So thanks for watching and have a nice rest of your day.
How do we overcome the limitations of traditional machine learning and learn how to solve more complex problems? Deep learning is a new type of data-driven AI. It stacks multiple layers of machine learning models one on top of the other. This allows it to learn more complex inputs and produce more complex outputs. We typically create deep learning models using a neural network. A neural network is a graph of nodes and edges based roughly on the organization of neurons in an organic brain. The nodes represent neurons in the brain. The edges represent the connections between the neurons. First, we feed data into the neural network via its input neurons. Next, mathematical operations are performed on the data in each of the neurons. Then, each neuron forwards its resulting value to all of the other neurons that it's connected to. We repeat this process for all of the nodes in the hidden layer of the network, as well as all of the edges in the hidden layer. Finally, the network produces a prediction from its output neurons. There's a bit of math involved to make this entire process work. However, we're going to skip over all of the math to keep things simple. A deep neural network is a neural network with more than one hidden layer. Adding more hidden layers allows the network to model progressively more complex functions. For example, imagine we wanted to teach a deep neural network how to detect human faces. First, we'd feed a set of labeled images into the input layer of this network. We'd do this to teach the network the faces of each person and their corresponding name. The first layer of the neural network would learn to detect geometric primitives, for example, horizontal, vertical, and diagonal lines. The second hidden layer would learn to detect more complex facial features, for example, eyes, noses, and mouths. The third hidden layer would learn to detect the general pattern for entire faces. The output layer would detect the most abstract representation of a person, in this case, the name of the person being recognized. Each layer learns to extract more complex features from the preceding layer. As a result, the data becomes more abstract with each additional layer in the network. To learn more, please click the link in the description. For more content like this, please be sure to like, share, and subscribe.
When it comes to AI, machine learning, and deep learning, there is some confusion as to what these words mean and the differences between them. So in this video, we will explain what AI means and how to differentiate between these three terms. So what is artificial intelligence? In the broader sense of the word, artificial intelligence refers to a machine that is made to simulate human consciousness. When the average person thinks of AI, they imagine robots that can see, move, speak, think, and possibly even feel the way humans do. For some, the ultimate goal of AI research is to create a sentient conscious being through programming. Sometimes this is also referred to as artificial general intelligence. However, in practice, most data scientists are using AI at a smaller, more practical scale to solve real-world problems, such as data analysis, manufacturing, and customer service. In that sense, AI is the umbrella term for technology that solves problems autonomously by simulating human intelligence. They do this through algorithms designed to analyze input data and produce an output. Using chatbots, for example, the input data would be the customer's inquiry, and the output would be the answer to the customer's inquiry held within the chatbot's database. What's more amazing is that AI algorithms can react to input data in various forms. A great example is how you would ask a virtual assistant like Amazon Alexa or Google Assistant for the weather report. There are multiple ways that you could phrase that query. For example, what's the weather, what's the temperature, or even how's the weather looking? But by picking up on certain keywords, the virtual assistant can respond to all these different variants.
The current weather is 23 degrees Celsius with clear skies.
So if that's the definition of AI, then how is machine learning different? Well, machine learning is generally considered to be a subset of AI. However, it's pretty common to hear the two terms used interchangeably. One major difference is that while AI still encompasses the idea of a sentient, conscious machine, machine learning as a term does not hold those connotations. AI is the grand vision of intelligent machines, while machine learning consists of the models, processes, and supporting technology that we've been using to get there. Diving a bit deeper now, within machine learning is another sector known as deep learning. In a nutshell, deep learning is machine learning at the largest scale, involving millions of instances of training data and often multiple layers within the neural network. As computing power and access to training data has increased, researchers have been able to develop machine learning models on a larger scale than ever before. Eventually, this led to the use of a new term, deep learning. To fully understand its meaning, it's essential to first know a little bit about neural networks. Simply, a neural network is a collection of algorithms designed to take in data and find a solution with the least amount of error. They are called neural networks because the design of the nodes, inputs, and outputs, which slightly resemble that of a neuron in the human brain. The key differentiator between machine learning and deep learning is in the number of layers of nodes that the input data passes through. In the past, it was only possible to connect a few layers of nodes due to simple computing limitations. However, as technology has improved, it has become possible to build deeper neural networks with more hidden layers. This is the kind of model that data scientists mean when they talk about deep learning. To sum things up, AI is the grand, all-encompassing vision of intelligent machines, and machine learning is the processes and tools that are getting us there. Finally, deep learning is machine learning at the largest scale, with more sophisticated neural networks, exponentially larger datasets, and stronger computing power supporting it. With this in mind, it's possible to begin navigating through this complex, exciting field and figuring out which processes will help to build out your own project. Thank you for watching Machine Learning 101. If you liked what you saw, please help us out by liking the video. And for more machine learning tutorials under 5 minutes, please hit the subscribe button below. That's all.
Training a computer to learn like a human brain. That's deep learning. Sometimes referred to as deep neural networking or deep neural learning, it's associated with artificial intelligence. And through deep learning, computers learn to recognize patterns and identify abstract objects. To understand deep learning, imagine a toddler learning about dogs. Let's say the toddler learns about dogs by pointing to objects, with the parents replying, yes, that is a dog, or no, that is not a dog. As the toddler continues to point to objects, he or she becomes more aware of dog features, like a tail and ears, and fur and 4 paws. The toddler is clarifying a complex abstraction, the concept of a dog, by building a hierarchy of which each level of abstraction is created with knowledge that was gained by the preceding layer of the hierarchy. If you've ever seen a program that can recognize a flower species based on a photo, or a song based on the sound of someone humming it, that is a result of a neural network. Beyond image and song recognitions, deep learning applications can be found in speech recognition and translation software, and even self-driving cars. Deep learning has its limitations, however. Deep learning models learn through observation, and they only know what they're trained on. A deep learning model trained on a small or irrelevant dataset will learn in ways that aren't ultimately useful to the task at hand.
Here are 5 things to know about neural networks in under 5 minutes. Number 1, neural networks are composed of node layers. There is an input node layer, there is a hidden layer, and there is an output layer. And these neural networks reflect the behavior of the human brain, allowing computer programs to recognize patterns and solve common problems in the fields of AI and deep learning. In fact, we should be describing this as an artificial neural network, or an ANN, to distinguish it from the very unartificial neural network that's operating in our heads. Now, think of each node or artificial neuron as its own linear regression model. That's number 2. Linear regression is a mathematical model that's used to predict future events. The weights of the connections between the nodes determines how much influence each input has on the output. So each node is composed of input data, weights, a bias or a threshold, and then an output. Now, data is passed from one layer in the neural network to the next in what is known as a feed-forward network. Number 3. To illustrate this, let's consider what a single node in our neural network might look like to decide, should we go surfing? The decision to go or not is our predicted outcome, or known as our y-hat. Let's assume there are 3 factors influencing our decision. The wave's good, 1 for yes or 0 for no. The waves are pumping, so x1 equals 1 for yes. Is the lineup empty? Well, unfortunately not, so that gets a 0. And then let's consider, is it shark-free out there? That's x3. And yeah, no shark attacks have been reported. Now, to each decision, we assign a weight based on its importance on a scale of 0 to 5. So let's say that the waves, we're going to score that one. Yeah, no, this is important. Let's give it a 5. And for the crowds, that's W2. Not so important. We'll give that a 2. And sharks, well, we'll give that a score of a 4. Now, we can plug in these values into the formula to get the desired output. So y-hat equals 1 times 5 plus 0 times 2 plus 1 times 4, then minus 3, that's our threshold, and that gives us a value of 6. 6 is greater than 0, so the output of this node is 1. We're going surfing. And if we adjust the weights or the threshold, we can achieve different outcomes. Number 4. Well, yes, but number 4, neural networks rely on training data to learn and improve their accuracy over time. We leverage supervised learning or labeled data sets to train the algorithm. As we train the model, we'll want to evaluate its accuracy using something called a cost function. Ultimately, the goal is to minimize our cost function to ensure the correctness of fit for any given observation. And that happens as the model adjusts its weights and biases to fit the training data set through what's known as gradient descent, allowing the model to determine the direction to take to reduce errors, or more specifically, minimize the cost function. And then finally, number 5, there are multiple types of neural networks beyond the feed-forward neural network that we've described here. For example, there are convolutional neural networks, known as CNNs, which have a unique architecture that's well suited for identifying patterns like image recognition. And there are recurrent neural networks, or RNNs, which are identified by their feedback loops, and RNNs are primarily leveraged using time series data to make predictions about future events like sales forecasting. So, 5 things in 5 minutes. To learn more about neural networks, check out these videos. Thanks for watching.
Imagine a neural network as a kind of black box, which takes one or multiple inputs, like the sensors of a self-driving car, processing them into one or multiple outputs, like the controls for that car. The neural network itself consists of many small units called neurons. These neurons are grouped into several layers. Neurons of one layer interact with the neurons of the next layer through weighted connections, which really are just connections with a real valued number attached to them. A neuron takes the value of a connected neuron and multiplies it with their connection's weight. The sum of all connected neurons and the neuron's bias value is then put into a so-called activation function, which simply mathematically transforms the value before it finally can be passed on to the next neuron. This way the inputs are propagated through the whole network. That's pretty much all the network does. But the real deal behind neural networks is to find the right weights in order to get the right results. This can be done through a wide range of techniques, such as machine learning. However, that's a topic for another minute.
So to continue our discussion on basics of the neural networks, we were able to watch the three previous videos about artificial neurons and neural network architecture. So artificial neurons, no, these are the fundamental processing units in neural networks. It is designed to replicate the behavior of biological neurons. No? These computational units simulate the way neurons in the human brain work, receiving inputs, processing them with assigned weights, and producing an output. The activation function often applied after the weighted sum. Nakita niyo yung computation kanina sa video, di ba? And introduces nonlinearity, allowing the network to model complex relationships in data. So again, no, these artificial neurons mimic, copy, replicate kung ano man ang meron sa ating biological neurons sa ating brains. Okay? So they accept or receive inputs and then ipina-process siya, no, depende sa mga weights na meron, and then it will now produce an output. So that's how artificial neurons work. No? We have here examples of artificial neurons, the perceptrons and sigmoid neurons. When we say perceptrons, no, ang characteristic niya, it is the simplest form of artificial neuron. It is developed by Frank Rosenblatt in 1957. And its function, it makes binary decisions. No? It's either 1 or 0. Diba? Ganun naman sa mga computer natin. It's binary. So it's 1 or 0. And based on a weighted sum of inputs and a threshold. So limitations ito, limited to solving linearly separable problems. On the other hand, we have here the sigmoid neurons introduces nonlinearity with the sigmoid activation function. No? It produces continuous output values between 0 and 1, making it suitable for binary classification problems. Okay? Example situations in image recognition. In image recognition, artificial neurons play a vital role in identifying patterns. Okay? So these artificial neurons in image recognitions identify patterns. It identifies features within images. For example, na-identify ng ng ating deep learning yung algorithm natin yung features ng pusa. Ang feature ng pusa, matulis yung tenga, no? Tapos yung feature naman ng ibon, meron siyang tuka, 'di ba? Meron siyang pakpak. So that's how these neurons identify patterns and features na within images. For example, no, edge detection. Artificial neurons help in recognizing edges, yung mga kanto-kanto, edges, which are crucial features in image processing. Now, neurons analyze pixel, no, and intensities and identify abrupt changes indicating the presence of edges. Next one, in image recognition, we have here the shape recognition. Artificial neurons contribute to recognizing complex shapes within images. For example, yung shape ba ng ulo ng pusa, ang bilog, halimbawa. Shape ng ulo ng aso, di ba? Medyo pahaba. So that's how this helps in image recognition. So artificial neurons, in summary, artificial neurons in the context of image recognition act as sophisticated pattern detectors. Okay, so these artificial neurons is being used to detect sophisticated patterns. Okay, so through training on large data sets, neural networks with these neurons, yung neurons, ito artificial neurons na to, can learn to recognize complex visual features, allowing them to distinguish between objects, shapes, and structures within images. The hierarchical arrangement of layers in neural networks enables the gradual abstraction of features, contributing to the network's ability to understand and interpret visual information. Okay, the flexibility of artificial neurons allows neural networks to adapt and excel in tasks beyond image recognition, showcasing the versatility and power of this computational paradigm in various domains. So, to further understand artificial neurons, okay, let us again watch the following videos that I have prepared for you.
In this video, we'll be discussing artificial neural networks. In the previous video, we defined deep learning as a subfield of machine learning that uses algorithms inspired by the structure and function of the brain's neural networks. As such, the models used in deep learning are called artificial neural networks. So put simply, artificial neural networks are computing systems that are inspired by the brain's neural networks. These networks are based on a collection of connected units called artificial neurons, or simply just neurons. Each connection between these neurons can transmit a signal from one neuron to another, and the receiving neuron then processes the signal and then signals downstream neurons connected to it. Typically, neurons are organized in layers. Different layers may perform different kinds of transformations on their inputs, and signals essentially travel from the first layer, called the input layer, to the last layer, called the output layer. Any layers between the input and output layers are called hidden layers. So now that we have the idea of the definition, let's just take a look at what one of these artificial neural networks may be illustrated as. I have another tab here opened in Google, and I just Googled images for artificial neural network, and here's one that I think does a pretty good job explaining what we just went over. So I said that the first layer would be called the input layer, so these would all be our inputs. They would then be transferred to a hidden layer here, and now this hidden layer has 4 different neurons. Each one of these nodes here illustrates a neuron, and them together within this column represent a layer. Since this layer is between the input and output layer, it is a hidden layer. And then from this hidden layer, these nodes transmit signals down to the nodes in the output layer. So now that we understand what an artificial neural network is and how it's depicted, let's see how we can build one. As mentioned when we went through the introduction of this entire playlist, I stated that I'll be using the neural network API called Keras, which is written in Python, to show code examples of the topics we cover here. So in Keras, we can build what is called a sequential model. Keras defines this sequential model as a linear stack of layers. And recall, we just mentioned that neurons are organized in layers, so that makes sense for a naming scheme. So this sequential model will be Keras' implementation of an artificial neural network. So let's have a look at how a very simple sequential model would be built in Keras. Assuming that you have Keras installed, you would first import sequential from keras.models, and then you would also need dense and activation from keras.layers, and we'll cover what these actually mean. So I'm creating a variable here called model. I'm setting it equal to an instance of a sequential object. Now within the constructor, I'm passing this array, and this array has 2 dense objects. Now these objects called dense are actually layers. Now dense is just a type of layer, and there are many different types of layers, and in later videos we'll cover more details about what exactly a dense layer is and what other types of layers there are. But for now, just understand that dense is the most basic type of layer within a neural network, and it connects each input to each output within the layer. So before moving forward, let's just flip back to our image here, and this layer here, this hidden layer, would be considered a dense layer, and that's because it's connecting all of its inputs here to each output node within the layer. So we have our model object set to an instance of sequential that's taken in an array of 2 dense layers, and within our dense layer, the first parameter that we're specifying, this 32 for example in our first layer, is the number of nodes or neurons within our layer. The second parameter, input shape here, is going to be the shape of our data that we're passing into our model. And then lastly, this activation function is something that we're going to talk about in more detail later, but for now you should just know that an activation function is typically a nonlinear function that follows a dense layer. The next layer here is also a dense layer. This time it only has 2 neurons, and it's using a different type of activation function. So one thing to note here is that we're showing this very basic model in Keras just to get started, but for more technical videos specifically on Keras, be sure to watch my Deep Learning with Keras playlist on my channel. So hopefully now you have an idea of what an artificial neural network is and how you can build one using Keras. And I hope you found this video helpful. If you did, please like the video, subscribe, suggest, and comment. And thanks for watching.
You are currently watching an artificial neural network learn. In particular, it's learning the shape of an infinitely complex fractal known as the Mandelbrot set. This is what that set looks like, complexity all the way down. Now, in order to understand how a neural network can learn the Mandelbrot set, really how it can learn anything at all, we will need to start with a fundamental mathematical concept. What is a function? Informally, a function is just a system of inputs and outputs, numbers in, numbers out. In this case, you input an x and it outputs a y. You can plot all of a function's x and y values in a graph where it draws out a line. What is important is that if you know the function, you can always calculate the correct output y given any input x. But say we don't know the function, and instead only know some of its x and y values. We know the inputs and outputs, but we don't know the function used to produce them. Is there a way to reverse engineer that function that produced this data? If we could construct such a function, we could use it to calculate a y value given an x value that is not in our original dataset. This would work even if there was a little bit of noise in our data, a little randomness. We can still capture the overall pattern of the data and continue producing y values that aren't perfect, but close enough to be useful. What we need is a function approximation, and more generally, a function approximator. That is what a neural network is. This is an online tool for visualizing neural networks, and I'll link it in the description below. This particular network takes two inputs, x1 and x2, and produces one output. Technically, this function would create a three-dimensional surface, but it's easier to visualize in 2 dimensions. This image is rendered by passing the xy coordinate of each pixel into the network, which then produces a value between -1 and 1 that is used as the pixel value. These points are our dataset and are used to train the network. When we begin training, it quickly constructs a shape that accurately distinguishes between blue and orange points, building a decision boundary that separates them. It is approximating the function that describes the data. It's learning, and is capable of learning the different datasets that we throw at it. So what is this middle section then? Well, as the name implies, this is the network of neurons. Each one of these nodes is a neuron, which takes in all the inputs from the previous layer of neurons and produces one output, which is then fed to the next layer. Inputs and outputs sounds like we're dealing with a function. Indeed, a neuron itself is just a function, one that can take any number of inputs and has one output. Each input is multiplied by a weight, and all are added together along with a bias. The weights and bias make up the parameters of this neuron, values that can change as the network learns. To keep it easy to visualize, we'll simplify this down to a 2-dimensional function, with only one input and one output. Now, neurons are our building blocks of the larger network, building blocks that can be stretched and squeezed and shifted around, and ultimately work with other blocks to construct something larger than themselves. The neuron, as we've defined it here, works like a building block. It is actually an extremely simple linear function, one which forms a flat line, or plane when there's more than one input. With the 2 parameters, the weight and bias, we can stretch and squeeze and move our function up and down and left and right. As such, we should be able to combine it with other neurons to form a more complicated function, one built from lots of linear functions. So let's start with a target function, one we want to approximate. I've hard-coded a bunch of neurons whose parameters were found manually, and if we weight each one and add them up, as would happen in the final neuron of the network, we should get a function that looks like the target function. Well, that didn't work at all. What happened? Well, if we simplify our equation, distributing weights and combining like terms, we end up with a single linear function. Turns out, linear functions can only combine to make one linear function. This is a big problem, because we need to make something more complicated than just a line. We need something that is not linear, a non-linearity. In our case, we will be using a ReLU, a rectified linear unit. We use it as our activation function, meaning we simply apply it to our previous naive neuron. This is about as close as you can get to a linear function without actually being one, and we can tune it with the same parameters as before. However, you may notice that we can't actually lift the function off of the x-axis, which seems like a pretty big limitation. Well, let's give it a shot anyway and see if it performs any better than our previous attempt. we're still trying to approximate the same function, and we're using the same weights and biases as before, but this time we're using a ReLU as our activation function. And just like that, the approximation looks way better. Unlike before, our function cannot simplify down to a flat linear function. If we add the neurons one by one, we can see the simple ReLU functions building on one another, and the inability for one neuron to lift itself off the x-axis doesn't seem to be a problem. Many neurons working together overcome the limitations of individual neurons. Now, I manually found these weights and biases, but how would you find them automatically? The most common algorithm for this is called backpropagation, and is in fact what we're watching when we run this program. It essentially tweaks and tunes the parameters of the network bit by bit to improve the approximation, and the intricacies of this algorithm are really beyond the scope of this video. I'll link some better explanations in the description. Now we can see how this shape is formed, and why it looks like it's made up of sort of sharp linear edges. It's the nature of the activation function we're using. We can also see why, if we use no activation function at all, the network utterly fails to learn. We need those nonlinearities. So what if we try learning a more complicated dataset, like this spiral? Let's give it a go. Seems to be struggling a little bit to capture the pattern. No problem. If we need a more complicated function, we can add more building blocks, more neurons and layers of neurons, and the network should be able to piece together a better approximation, something that really captures the spiral. It seems to be working. In fact, no matter what the dataset is, we can learn it. That is because neural networks can be rigorously proven to be universal function approximators. They can approximate any function to any degree of precision you could ever want. You can always add more neurons. This is essentially the whole point of deep learning, because it means that neural networks can approximate anything that can be expressed as a function, a system of inputs and outputs. This is an extremely general way of thinking about the world. The Mandelbrot set, for instance, can be written as a function and learned all the same. This is just a scaled-up version of the experiment we were just looking at, but with an infinitely complex dataset. We don't even really need to know what the Mandelbrot set is. The network learns it for us, and that's kind of the point. If you can express any intelligent behavior, any process, any task as a function, then a network can learn it. For instance, your input could be an image, and your output a label as to whether it's a cat or a dog. Or your input could be text in English, and your output a translation to Spanish. You just need to be able to encode your inputs and outputs as numbers, but computers do this all the time. Images, video, text, audio, they can all be represented as numbers, and any processing you may want to do with this data, so long as you can write it as a function, can be emulated with a neural network. It goes deeper than this though. Under a few more assumptions, neural networks are provably Turing complete, meaning they can solve all of the same kinds of problems that any computer can solve. An implication of this is that any algorithm, written in any programming language, can be simulated on a neural network. But rather than being manually written by a human, it can be learned automatically with a function approximator. Neural networks can learn anything. Okay, that is not true. First off, you can't have an infinite number of neurons. There are practical limitations on network size and what can be modeled in the real world. I've also ignored the learning process in this video and just assumed that you can find the optimal parameters magically. How you realistically do this introduces its own constraints on what can be learned. Additionally, in order for neural networks to approximate a function, you need the data that actually describes that function. If you don't have enough data, your approximation will be all wrong. It doesn't matter how many neurons you have or how sophisticated your network is, you just have no idea what your actual function should look like. It also doesn't make a lot of sense to use a function approximator when you already know the function. You wouldn't build a huge neural network to, say, learn the Mandelbrot set when you can just write 3 lines of code to generate it. Unless, of course, you want to make a cool background visual for a YouTube video. There are countless other issues that have to be considered, but for all these complications, neural networks have proven themselves to be indispensable for a number of really rather famously difficult problems for computers. Usually, these problems require a certain level of intuition and fuzzy logic that computers generally lack, and are very difficult for us to manually write programs to solve. Fields like computer vision, natural language processing, and other areas of machine learning have been utterly transformed by neural networks. And this is all because of the humble function, a simple yet powerful way to think about the world. And by combining simple computations, we can get computers to construct any function we could ever want. Neural networks can learn almost anything.